Okay, let's take a crack at sac124 problem number 1. We've got a marble fired from a spring-loaded gun, which is initially cocked. They want to know how fast the marble is going when it leaves the gun and how high above the ground the marble goes. We've actually got two after pictures, one for part A, one for part B. So rather than just draw a before and after, I'm going to draw a series of 3 diagrams. I use the same reference level for all 3 diagrams, the ground level. I call that the y is equal to 0 reference level. So normally in a conservation of energy problem, we'll just draw a before and after picture. Here, with 2 after situations, I'm going to draw a series of pictures, 3 pictures. Picture number 1 will have initial conditions. You got the spring is compressed. Marble resting on top of the spring. And we're given some data on it. We'll call the initial height above the ground y1. That's given as 38.6 centimeters or 0.386 meters. And then the amount by which the spring is compressed says as the ball leaves the gun, the spring is at its unstretched, uncompressed length. Right here, the marble exits the gun just as the spring achieves its unstretched, uncompressed length. So initially, this distance in the picture represents the amount by which the spring is compressed. And that's given up here as 25.2 centimeters. I'll call it 0.252 meters. I'm using the subscript 1 to represent the situation. In picture 1, we've got 0 velocity. And that probably does it for picture number 1. Let's do picture number 2. This will be my after picture for part A. You want to know how fast it's going when it leaves the gun, so we'll have the marble at the exit of the spring-loaded gun. In this picture, the spring is uncompressed. Again, because they said that it achieves its unstretched, uncompressed length just as the marble leaves the gun. The marble is moving. With a speed I'll call V2. So uncompressed spring means X2 is equal to 0. But Y2 is not 0 at all. That'll be all the way from here on up. Let's see, what is Y2? We got Y2 is going to be the sum of these 2 distances. Y1 plus X1. And that's 0.386 meters plus, that's an equal sign right there. Let me emphasize that. Write it a little bit more clearly. Plus the 0.252. And that adds up to 0.638 meters. Alright, so Y2 is 0.638 meters. Alright. Then in picture number 3, we've got the ball has gone to its maximum height. I want to know how high it goes. That's another way of saying what's the maximum height achieved by the marble. Again, the spring is not touching the marble, so we don't really care whether it's stretched or compressed, but we'll list it as having a compression of 0. The marble we'll put up here at its maximum height with 0 velocity. So I'll call that V3. That's the speed or magnitude of the velocity in picture number 3. And it's 0 at the top. So it had some upward velocity, which was decreasing the whole way up, and then it achieves 0 velocity at the top, and after that it's going to start picking up a downward velocity as a result of the gravitational influence of the Earth on it. We'll call this height Y3, and it's Y3 that we're solving for in part B. Okay, we've got enough diagrams to get going. For part A, we'll use number 1 as the before picture and number 2 as the after picture to find out V2 in picture number 2. So I'll say E1 is equal to E2, which tells the reader I'm applying conservation of energy, and I'm using 1 as the before situation, 2 as the after situation. E consists of the kinetic energy plus gravitational potential energy plus spring potential energy. And that's all for picture number 1. And get the same situation for picture number 2. Alright, let's think about what's 0 and just cross it out, indicate to the reader that it is 0. The object is at rest in picture number 1, so there is no kinetic energy. Kinetic energy is energy of motion, there's no motion. Alright, for the gravitational potential energy to be non-zero, it's going to be up high with respect to the reference level. The marble is up high. And for the spring potential energy to be non-zero, the spring has to be stretched or compressed, and indeed it is compressed in amount x1, so neither of those is 0. In the after picture, we definitely have some velocity, so we do have some energy of motion. It's V2, the velocity at the muzzle of the gun that we're seeking. It is still up high. In fact, it's higher than it was a while ago. But the spring is no longer compressed. It's at its unstretched, uncompressed length in picture number 2. So that's 0. Now we'll go ahead and replace these symbols for energy with expressions for energy. The potential energy associated with the gravitational force is mg times the height, which in picture number 1 is y1. And the spring potential energy is 1/2 the spring constant k times the amount of stretch or compression, which in this case squared, which in this case is going to be x1 squared. That's all equal to kinetic energy in the picture number 2, 1/2 mv2 squared, plus gravitational potential energy in picture number 2. Okay, and we're solving for V2 here, so now it's just a question of doing some algebra. I think I'll first subtract mgy2 from both sides and at the same time switch sides. So after subtracting that, all I have left on the right is 1/2 mv2 squared. I'm going to write that on the left. And on the right, I'll write the MGY1 that was originally on the left, and the MGY2 that's being subtracted from both sides with a minus sign over here, and then the 1/2 kx1 squared. Alright, I'm going to multiply both sides by 2 over m to get rid of this 1/2 m here. That'll give me a v2 squared. 2 over m times this term leaves 2gy1. And 2 over m times this term leaves 2gy2. And 2 over m times this term leaves k x1 squared over m. So now I just have to take the square root of both sides to get v2. That leaves v2. It's going to be the square root of 2. I think I factor out the 2g from these first two terms at the same time. y1 minus y2, and then plus k x1 squared over m. So at this stage I just have to substitute the values in there. 2 times 9.80 kilograms per Newton is our gravitational force constant, times y1 minus y2. That's 0.386 meters minus 0.638 meters. Plus the spring constant, or the force constant for the spring, given as 10.2 newtons per meter. Times the amount of compression in picture number 1, that's the 0.252 meters. And that's going to be squared. All divided by the mass of the marble, given up here as 17.0 grams, or 0.0170 kilograms. And substituting that into the calculator, I get 5.76 meters per second. For the speed / magnitude of the velocity of the marble as it exits the gun. That's the answer to part A. Let's take a look at part B. They want to know how high above the ground the marble goes. To get that, I'll move over a little bit. I'm going to use picture number 1 as the before picture. So I go E1 is equal to E3. Energy in this picture is going to be equal to the energy in this picture. I could have used E2 is equal to E3 if I wanted, but E2 involves a calculated quantity, the V2. E1 involves all given quantities, so I'd rather go all the way back to picture number 1 for this part. So again, I can actually copy this part. I get kinetic energy plus gravitational potential energy plus the spring potential energy. Copy in front of, over there, the kinetic energy is 0, where I know that because the velocity is 0. And then in the after picture, I've got same kind of energy possibilities. Call it K3 plus UG3 plus US3. Kinetic energy, gravitational potential energy, spring potential energy. And as far as what's 0, it's not moving at the very top. Dimension V3 is equal to 0. So the kinetic energy is 0. It is up high. In fact, it's up very high. So that's not 0. But the spring is neither stretched nor compressed. It's not even involved at this point in the motion of the marble. It was, but no longer is involved in the motion of the marble. Alright, let's go ahead and replace these symbols with expressions representing them. I've got mg y1 plus 1/2 k x1 squared. This is, of course, a lowercase k, whereas the uppercase k was used for kinetic energy. And that's equal to mg times the height in the after picture, which we've called y3. And in fact, it's y3 that I'm solving for. I think I'll divide both sides by mg and switch sides at the same time. So I'm left with y3, originally on the right, now writing that on the left. And then this term divided by mg just leaves the y1. And this term divided by mg leaves, I'll write it as k x1 squared over 2mg. So just have to substitute values in there with units. I get y3 is equal to y1, which was the 0.386 meters, plus the spring constant was 10.2 newtons per meter, and still is. The amount of compression was 0.252 meters, and still, well, that was the amount of compression in the before picture. That's got to be squared, and then we've got 2, and the mass was 17 grams or 0.0170 kilograms. And the gravitational force constant is 9.80 newtons per kilogram. So we substitute those values into the calculator and evaluate. We find y3 is 2.33 meters. It's the maximum height achieved by the marble. It's the answer to the question, how high does the marble go?